So let's look at an example. Let's say f of x equals, how about x squared plus 1 divided by x squared minus 1. That seems like a simple enough function, right? And why don't we do this? Identify horizontal and vertical asymptotes. Which would you all like to do first? Horizontal is first alphabetically. Why don't we do that? How do I find the horizontal asymptotes of a function? Yeah, I can look at the end behavior of this function, right? The idea is to take the limit as x approaches infinity of that function, x squared plus 1 over x squared minus 1. And in general, I also want to test what happens as I approach negative infinity. Although with rational functions, it'll always be the same. And the shortcut for this is to look at the highest powers, right? The highest power is 2, the highest power is 2. This is an infinite limit, so I can take these leading coefficients. I can imagine that at infinity, all of the other bits of these functions don't matter. This looks like x squared divided by x squared, which is 1. At negative infinity, similarly, right? These x squareds, these leading terms, are bossing the function around. The end behavior for this function is going to look like x squared divided by x squared. I can just look at these leading coefficients, 1 and 1. So that's 1. They're both the same. So if I were to sketch this function, I know that all the way left, it looks like 1. And all the way right, it also looks like 1. I don't know whether it's above or below this line, but I know that it's roughly on this line, one direction or the other. And then there's going to be function in between. What about vertical asymptotes? How do you identify these? Yeah, these, the key aspect is that you have a number divided by 0. So I'm going to take the denominator and I'm going to set it equal to 0. That means that x minus 1 times x plus 1 is 0, which means that either x minus 1 equals 0 or x plus 1 equals 0. Remember, anytime you have a product equal to 0, one of the factors must be 0. If x minus 1 is 0, that means that x is 1. If x plus 1 is 0, that means that x is negative 1. So these are my two suspects for vertical asymptotes. The last thing that I would want to do is I would want to plug them into the numerator to make sure that I got a real number that was non-zero. If I plug 1 in, I get 2. If I plug negative 1 in, I also get 2. So that's enough assurance to me that I'm not getting 0 over 0, but that I instead have a real number divided by 0, a non-zero number divided by 0. So 1 and negative 1. So if I wanted to sketch this thing, I know that at 1 and negative 1, it looks like these vertical lines. If I got a little thinky about it, I could probably figure out whether it was really big or really small on each side of these vertical lines. But in order to graph this function, I don't have to get that thinky about it. Because let's ask ourselves another interesting question. when is this function increasing and when is it decreasing? So here's our function up here. Right? When is f increasing? Decreasing? How do I find that out? I could just, wildly plug in numbers and see what's happening, but that seems painful. And it seems like it's an easy way for me to miss things. Right? What if something important happened between the numbers that I just guessed and checked at? Come on, guys. I gave you a checklist at the beginning, and I was like, hey, everybody feels good about this stuff. And you all said, When is it increasing? When is it decreasing? What would it mean for a function to be increasing in calculus terms? Yeah, the slope would have to be positive. And what measures the slope? The derivative, right? So it's increasing if the derivative is positive. And it's decreasing if the derivative is negative. Right? Increasing, decreasing have to do with the derivative. So we better find what that is. Let's see, it's a quotient, right? So low d high minus high d low divided by the square of what's below. Okay? So here's the derivative. The bottom function times the derivative of the top function minus the top function times the derivative of the bottom function divided by the bottom function squared. Low d high minus high d low over the square of what's below. There we go. Now I can use a little bit of algebra here. I can distribute these two x's. So I get 2x cubed minus 2x minus 2x cubed minus 2x, all divided by x squared minus 1, the quantity squared. Those 2x cubes cancel. The 2x cubes cancel. I still have this. I still have the 2x's. So that's negative 4x divided by x squared minus 1, the quantity squared. All right, so what am I going to do with f prime in order to find out when it's positive and when it's negative? I don't want to plug in 0. Right? I'm not interested in what the derivative is at 0. I'm interested in when the derivative is 0. Right? So how would I find that? Yeah, we'll set it equal, right? Because when it is 0, those are times when it might be changing from positive to negative or vice versa, right? To go from positive to negative or from negative to positive, you've got to move through 0 to get there. So by finding those 0 times, I can break up sections of when it's positive and when it's negative. So find when f prime of x equals 0, and what are the other times? What else could happen that would make a function go from positive to negative? You could just pick up your pen and move it, right? What would happen on the graph there, though? You'd have a does not exist for the derivative, right? So f prime of x does not exist. These are called critical values. Critical values are both of these things. In applications of derivative, it's what do we do tonight, Pinky? The same thing we do every night, right? Except, what do we do tonight, brain, right? Pinky said it. Right? You do the same thing all the time. You take the derivative, you set it equal to 0. Because I want to know when the derivative is 0 or when the derivative does not exist. These are the critical values. These are the usual suspects for us in applications of derivatives. because these are the times when change happens. These are the times when you stop increasing and start decreasing. These are the times when you have maxima and minima. This is the interesting stuff. So I'm going to take negative 4x divided by x squared minus 1, the quantity squared, and I'm going to set it equal to 0. When is that equal to 0? How do you get 0 out of a fraction? Yeah, only if the top is 0. So negative 4x equals 0. That means that x is 0. That's easy enough. Why would this not exist? Division by 0. So x squared minus 1 squared equals 0. This factors well enough. I knew how to factor x squared minus 1 before, right? It's x plus 1, x minus 1. So x plus 1, x minus 1 squared is x plus 1 squared, x minus 1 squared. That means that x is negative 1 or x is positive 1, just like before. In our picture, that means that the function can stop increasing and start decreasing at these asymptotes. So I'm not surprised to find that those are interesting times. Those are times that the behavior might change because it's asymptotic at those times. All right. So I have these 3 critical values, and what do I do with them? What's that? Nah. I'd be able to find out what the concavity was. So I'd be able to kind of tell whether it was concave down or concave up at those times, except for positive 1 and negative 1 because the function doesn't exist there. So I might be able to use that to decide whether this time x equals 0 is a max or a min, because if it were bowed down, I would know that it was a max, and if it were bowed up, I would know that it was a min. But that's not going to tell me whether it's increasing or not, right? Increasing, decreasing is all about f prime. It's all about whether f prime is positive or negative. So I know that it's not positive or negative at 0. I know it's not positive or negative at 1. And I know it's not positive or negative at negative 1. But I do know that these are the times that the derivative might change. So that's telling me that all of these points over here, all of the points less than negative 1, they're all either positive or negative. They're not both. They're all either all positive or all negative. It can't be a mixture of both because the only time that you could change are at these 3 times. So over here, how do I decide whether the function has a positive slope or a negative slope? Huh? Absolutely, right? How do you know what candy is in the candy jar? Well, you grab a piece and you taste it. Okay. So I'm going to pick my favorite number less than negative 1. Anybody have a favorite number less than negative 1? Negative 2 seems like a good choice. All right? And I'm going to plug it in. What am I going to plug it into? F prime, F double prime? F prime, right? Because I want to know, is F prime positive, is F prime negative? Right? I don't care about the other values. This is what's telling me about slope. F prime of negative 2. That's going to be negative 4, right? Negative 4 times negative 2 is 8. It's a positive number. Divided by negative 2 squared is 4. 4 minus 1 is 3. 3 squared is 9. 8/9. Do I care that it's 8/9? No. What do I care about then? Yeah, it's positive. Right? So over here, the derivative is positive. What does that tell me? It tells me the function's increasing. That's telling me on my function, right, it looks flat over here and it looks vertical over here, and in between, it's getting bigger. So I might imagine that the function looks like this. Yeah? Seems to make sense? And then I can go back and check all of the other times. I'll find that between -1 and 0, it's also positive. Between 0 and 1, it's negative, and between 1 and infinity, it's negative. And I can do that just by plugging sample values in. But I can tell what's happening by looking at the derivative, right? If I pick a number that is between 0 and -1, that's a small negative number. And if I plug it in, I'm going to get -4 times a negative number. So the top would look like positive. And divided by some number squared. And if you square a number, it's always positive. So here in this window between -1 and 0, it looks like a positive divided by a positive. This is one of the advantages of having your derivative factored, because if it's factored, you'll be able to tell the sign of the function without evaluating it and trying to figure out that it's 8/9 specifically. You can just say, oh, well, the top is going to be a positive number, the bottom is going to be a positive number, so that function will be plus divided by plus, which is plus. So back to this guy. I'm imagining that it's increasing, then it's decreasing, and then it's decreasing again. So here's a picture that follows that pattern. Increasing, increasing, decreasing, decreasing. And it fits the asymptotic behavior. How do I know how high to make this? It increases up to what? Why wouldn't this point be way up here? How could I find out where this maximum value is? Where does it occur? What's the x value where the maximum is? At 0. Why do we know 0 exactly? Why isn't it like -1 million? Could it be -1 million? No, right? Because it's increasing until you get to 0, and then it's decreasing. Here is where my maximum is. Because it increases, then it decreases. So it must have a max at 0. So if the maximum occurs at 0, that tells me why left to right the peak happens here. But how do I decide where to put that peak? Why doesn't this go way up and then way down? How can I know how high to make this? Yeah, f of x tells me that, right? F of x is where the function is. So if I plug 0 in for x, I get 1 over -1, which is -1. So that's how I know that it's down here. F of x is telling me that.
How come that top right quadrant is up there? Because if it's negative, should it be at the bottom?
The derivative is negative, which tells me that it's decreasing. And if I'm down here, I can't decrease and get to this line. Right? I know that it looks like this vertical line, and if I look like that vertical line right here, I have to get bigger in order to get up here. Right? I know that I end way off here on the right, and I begin on this vertical line. And if I'm decreasing, I must start up here to decrease down to this point. Does that make sense? Right. F prime of x is negative. That doesn't mean that f of x is negative. Right? F of x is negative means that you're down here. F prime of x is negative just means that you're getting smaller. Right? F prime negative, that happens here, but f prime negative also happens up here. F prime only tells us about the direction that the graph is headed in. It doesn't tell you where it is. So this all seems like pretty good stuff. What if I wanted to talk about concavity? What would I do? Yeah, we do the same type of thing with double prime. When is the second derivative positive? When is the second derivative negative? When is the second derivative equal to 0 or does not exist? And hopefully that would support the picture that we've already drawn. Based on this picture, when is the second derivative positive? What type of behavior does the second derivative being positive mean for the graph? It means concave up. So when is this function concave up? Less than -1, so over here, right, it's concave up. And then over here, it's concave up. So I'm expecting f double prime to be positive over here and over here. Less than -1 and bigger than +1. And then between -1 and 1, it's concave down, right? So I'm expecting f double prime to be negative in this window. And if I were to take the second derivative by using the quotient rule, and I were to set it equal to 0, I'd find that there were critical values at +1 and -1, and this is how it would break out. But it would be a big pain in the neck. Questions here? All right. So I want to be able to add this asymptotic behavior to my repertoire and be able to incorporate that into graph sketching. So this has something to do with limits. Do you all want to see where limits and derivatives tie together even more than they already were? It'll save you a bunch of time. One other thing then that I want to talk about today that's new. It's called L'Hopital's rule. L'Hopital rule. Yeah, it looks like La Hospital. That's because it's Old French. Sometimes you'll see it with other asterisks, but with inflection marks on the I's, like emphasis marks, and they'll drop this S, and they'll put in like they'll put in a dash over the O or something like that. I don't know. I always use this Old French La Hospital thing, but it's pronounced L'Hopital. French dude found out how to take the limit, how to evaluate the limit of indeterminate forms in an easy way that involves derivatives. Right. If the limit as x approaches a of f of x over g of x looks like 0 over 0 or infinity divided by infinity, if it looks like one of these two, then the limit as x approaches a of f of x over g of x is the same thing as the limit as x approaches a of f prime of x divided by g prime of x. You will notice that this is not the derivative of the function. It's the derivative of the top and the derivative of the bottom. So if we looked at that same function that we were looking at before, right, the limit as x approaches infinity of x squared minus 1 divided by 3x squared plus 2x plus 4. Right? This looks like something infinitely large divided by something infinitely large. Because polynomials follow the behavior of their leading terms, so this is going to look like 3x squared, which gets infinitely big. So it looks like infinity over infinity. L'Hopital tells me that this limit is the same as the limit of 2x divided by 6x plus 2. I can take the derivative of the top, which is 2x, and the derivative of the bottom, which is 6x plus 2, and these limits are exactly the same. You will note again that this is not the derivative of the function. This is not the way that we take the derivative of functions. We have to use the quotient rule for that, the low d high minus high d low stuff. You'll notice also that this still looks like infinity over infinity. But I know how to do this type of thing. It looks like infinity over infinity. L'Hopital says, take the derivative of the top, divide by the derivative of the bottom. And what happens to 2/6 as x approaches infinity? You get 2/6, right? If x can do whatever you want it to, 2/6 will still be 2/6. And 2/6 is just a fancy way of writing 1/3. So I used L'Hopital rule here, I used L'Hopital rule here, and then I got to a place where I could evaluate this limit. Seems like it makes sense? Yeah.
How did you, you took the rule the first time, you got 2x over 6x plus 2. How did you get from there to 2x?
From here to here?
You just plug infinity in?
No, well, this, I looked at this and I said, this still looks like something infinitely big, looks like infinity, divided by something infinitely big. It still looks like infinity over infinity. But I know that infinity over infinity things, I can use L'Hopital's rule. So I took the derivative of 2x, which is 2, and I took the derivative of 6x plus 2, which is 6. Yeah, so I just kept hitting it with derivatives until it didn't follow the rule anymore. It's not infinity over infinity anymore, so here we are. Similarly, we might see something like the limit as x approaches 1 of x cubed minus 1 divided by x minus 1. Anybody know how to factor x cubed minus 1? Whatever. I don't care. Right? Why? Because if I plug 1 in, it looks like 0 over 0. And I know that I don't have to be able to factor this. I can just use L'Hopital's rule. The derivative of x cubed minus 1 is 3x squared. The derivative of x minus 1 is 1. So what's the limit as x approaches 1 of 3x squared over 1? 3. Ta-da, done. I don't have to factor. I can just use L'Hopital's rule. It's a cannon, this thing, right? There's no finesse to it. It just hits things with a really big hammer. But it's a very powerful tool that uses derivatives, and it allows us to evaluate these tricky types of limits.